Right, we'll do another few of these. What else would you be at on a Saturday morning? So we'll look at 2014 equilibrium calculation, 9A and B. So in this one they give you the value of Kc. First bit of the question 9 was simply to write down the equilibrium constant expression, so our Kc. Remember it's the concentration in moles per litre for products over our reactants. The square brackets just denote what? The moles per litre. So the products is our nitrogen and our oxygen. Nitrogen times our oxygen. Keep the square brackets over NO. And don't do it, I always do. Don't forget that 2. The ratio here, remember, is 2 is to 1 is to 1. And that'll be needed in the calculation. Now they said in this calculation that Kc is equal to 20.25. So if you like, you could write down that so I don't forget it for the next bit. Now, part B, I'd always get in the habit of writing down the equation, your reversible reaction at the start, and then get your headings. Same headings all the time. Moles initially, so that means moles at the start. Change. Moles at equilibrium, so in the container. And then the last one, equilibrium concentration. That's where you get your square brackets. That brings it back to a litre. Then you got to cipher through and calculate the number of moles of nitrogen in the reaction mixture at equilibrium. So we want to work out the number of moles of N2. So if we're making this in a wee grid again, what we want to get is our N2, which is here, the moles at equilibrium of that. When 2 moles of nitrogen monoxide, there's our 2 moles there, decomposes, and that was it, because they give us the value of Kc. So the number of moles we have initially of nitrogen, 0, and oxygen, 0. The change, now this is where your ratio comes in, of 2 is to 1 is to 1. So concentration of our products are going to rise. Concentration of reactants is going to decrease. Now, here I would say, these will go up x. So if they go up x, because the ratio 2 is to 1, they go down twice as much, minus 2x. And then just work our way down. Moles at equilibrium, 2 minus 2x, x, and x. And did they give us the size of the container? No, they did not. So you just keep this answer. But if they said it's 10 litre container, you divide it by 10. Or 15 divided by 15, so on. Now fill these values in back up here. So in our Kc, which is N2, which is x, O2, which is x, over NO squared, 2 minus 2x squared. Horse in your value of the equilibrium constant, 20.25, x times x squared. Write that bracket out twice if you like. Split it up, multiply it, or you could do your maths thing. If you're good at maths, square the first, multiply the 2 together and double it, square the last. What I would simply do from here is just bring this up, times that, and then tidy her up. 420s, 81. To what? Was it 162? Plus 81x squared. Looking like my quadratic. Bring that over there. 80x squared minus 162x plus 81 is equal to 0. Now, I'll probably do my minus b formula there. So a is equal to 80. B is equal to minus 162, C is equal to 81, and then minus B plus or minus square root of B squared minus 4 C all over 2 times A. Just remember the pressure fraction at the start, have the squared outside the brackets of your B, put the minus inside the brackets, otherwise you may get a math error. 9/8. So that is a thing, 1.125. And then the other answer is 9/10. Both positive. Generally you get a minus and a positive and just automatically score at the minus. Now you've got to do a wee bit more thinking. This here's okay. 2 minus 2 times 0.9 will still give us a positive answer. 2 minus 2 times 0.9 still give us 0.2. Maybe if we fill in 1.125, we're ended up with a minus figure. So we ignore this and we take this. And then you go back. They wanted a concentration of nitrogen at equilibrium. Therefore, the concentration of nitrogen is 0.9. And that's that one. Right, we'll go on. 2013. Question 9C. So the first thing, write the equilibrium constant expression for this. So again, your products over your reactants. Your products is this. And don't forget the charges. From marking so many papers now, you always see ones, just don't bother putting in that 2 plus. Do products over your reactants. Marvellous. Next thing, a mixture of this many moles were allowed to blah 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 1 litre container. Get her teed up. So here, I'll write in my wee equation again. Do my headings. Moles initially change. Moles at equilibrium. And there's different versions of these. I heard one student on about rice. Moles at equilibrium. Equilibrium concentration. Probably about ratios and equilibrium or whatever. Our initial. Change and equilibrium it must have been. So, what do we have? A mixture of 1 by 10 to the minus 3 moles of iron 3 chloride. I don't like that. If you wanted your calculator in decimals, just go shift mode, 8 for Norman, and then 2. And then that, if I type in 1 by 10 to the minus 3, it gives me 0.001. So, we've got 0.001 moles initially of iron 3, using the oxidation numbers, and potassium thiocyanate. There's my KCNS. Generally, they give you your reactants. We're allowed to come to equilibrium. 1 litre container, which is lovely because it's going to be the same here. Room temperature, according to the equation, it was found that many moles were present at equilibrium. So we have 0 moles of this. Next thing you go to moles at equilibrium of this boy. And again, it's 1.1 by 10 to the minus 4. You type it in, press equals, it'll give you 0.00011. And going into your moles at equilibrium. So now we can fill in the rest. We can see the change. We went from 0 to that. So obviously that's increased by. And if the ratio here we can see is 1:1:1. So that went up by that amount. These values are going to go down by that amount. And then just subtract those figures. 0.001 minus that. 0.00089. I just prefer that rather than the scientific notation, but it's personal preference. And then we divide it by 1 and we get the same figure. So despite looking very awkward, it's not been the worst. And then for our KC, we fill these values back in up here. So 0.00011, no powers to put in them because there's no numbers in front of them. And there'll be a lovely little Lishiteye problems in this sort of question as well. But I'll go over those someday. Just do all the calculations here at the start. 138.87, so equilibrium very much on the right hand side. Right, we look, I suppose 2012. How many minutes? Yeah, so we'll go 2012 as well. Must have been in question 10 or 11. It's a part B. I'm not too sure what the question was. So consider the following room temperature for iodine. So you've got I2 plus I minus, giving you I3 minus your formation of your triiodide ions. You look at that there. In a redox reaction, excess potassium iodide, keep the iodine in solution during your bleach experiment, forming your polar I3 minus, so it's soluble in water, keeps it in solution. That's good enough. So 1.08 moles, we'll get teed up, do your headings, moles initially, so you do need to know that equation, moles initially, change, moles at equilibrium, equilibrium concentration. So when 0.08 moles of iodine and 0.24 moles of iodide ions, so different amounts even though the ratios are the same, so 0.24 moles of this, and we have 0 moles of that initially of our product. We're added to the ionized water, made up to a litre, 0.0793 moles were present at equilibrium. So moles at equilibrium of I3 minus or triiodide was 0.0793. Again, now we can work out the change. We went from 0 to that, so obviously we've increased by that. The ratio is 1:1, so we've decreased here by the same amount. Subtract those, you'll get 0.0007. Just to be sure, I'll take that away. I think it is 0.08 minus 0.000, yeah, and 0.24 minus 0.0793, 0.1607, and then it's a 1 litre container, so this is the same, or even if it doesn't give you the size of the container, treat it as the same because their volumes actually cancel. Now your Kc, equilibrium expression, products, keep your charge inside it, and then horse in the values. Bung that in your calculator now. That's 704.95. So again, equilibrium very much on the right hand side. 13 minutes. Well, probably we could do another one. In fact, well, we just do 2011. Presume all the rest are much the same. So 2011. And it's question 9A. So hydrogen iodide. So you got 2Hi H2 plus I2. Suppose you could get in the habit of writing down your ratio 2:1:1. You need to do it for your moles questions. Place in a sealed container, 700 Kelvin, just because it's temperature dependent. Blah, blah, blah. Write the equilibrium constant expression, so we'll do that first. Products over reactants. Oh, it doesn't matter what order I write them in. H2 times I2 over Hi. Don't forget your square. Calculate the equilibrium concentration. I'll get it teed up without reading any further. The moles initially. Doesn't matter what the type of calculation is. On equilibrium, I have the same thing. Moles initially change. Moles at equilibrium. And equilibrium concentration. Right, now look through. Calculate the equilibrium concentration of hydrogen gas when 5 moles of hydrogen iodide decompose. So you've got 5 moles here, 0 moles starting off of our product. 12 litre container, we'll not forget that 12 litres. That's all we've got to go by. The ratio 2:1 is very important. Remember, our product's going to go up it's going to go up X amount. So when they give you your KZ value, you're going to be working in X's, and this is going to go down double the amount of this, so that's going to go down minus 2x because of your ratio. Moles at equilibrium now is 5 minus 2x, x and x, and this is over 12. This won't be a nice one. X over 12, x over 12. Jeez, it will not. Right, what is our KC? The value of KC is 0.0185. I'll just fill it in up here. Now we've got to sub in these values in up here. We'll need another page. I'll do it here. So using them values, fill them in up here. So KC is equal to our H2 is x over 12, and our I2 is the same, x over 12, all over 5 minus 2x over 12 squared, which I always forget them sort of things. 5 minus 2x. Yeah, looks good enough. Now we know our KC is 0.0. When you're multiplying these out, top by top, bottom by bottom, x squared over 144, all over 5 minus 2x. Again, it's top by top, bottom by bottom. The power goes on each of them. So square the first, multiply the two together and double it, square the last over 144, and just bring all that bottom bit up there. I just put that over 1, so when I'm multiplying it, top by top, bottom by bottom, I know this is being multiplied by this, the two numerators. So 0.0185 by 25, so these aren't going to be nice numbers. 37 over 80, or 0.4625 by 20, 0.37. and by 4, 0.074 x squared over 144, multiply by your common denominator, which is 144. They both go. Bring her up here. You've got 0.4625 minus 0.37x plus 0.074x squared is equal to what? X squared. Bit of a mess here I'm making, but should be alright. Bring every term over to the right hand side. Keep your x squared positive, I prefer, so 1 minus that. 0.926 x squared plus 0.37x minus 0.4625. Not looking hectic. Now do your minus b in this. So a is 0.926, b is 0.37, c is equal to minus 0.4625. Throw it into your minus b. Minus b plus or minus square root of b squared. I would generally write out the formula, but I'm getting our tight for space. This shouldn't be the bother anyway if you're doing higher level chemistry. Call a spade a spade. Minus b squared minus 4ac all over 2a. And you mean you throw that in. X equal to 0.535 or 0.54. I just wouldn't round too early. And minus 0.93. Not going to take the minus because of these things here, these values of X here. And what did they ask you for? Calculate the equilibrium concentration of hydrogen gas. So equilibrium concentration of hydrogen gas is our X over 12. This is over H2 in moles per litre. That's why you're dividing by 12. And X is 0.53 over 12. 0.045, say, moles per litre, brings us back to your 1 litre. Right, hello.